And these, if you've seen them, are just dual graphs of stable curves equipped with edge lengths. But I won't assume any of that, and in fact, I'll start right now telling you what I mean by a curve and what a stable curve is. All right, so let's fix an algebraically closed field, little k. And by a curve, I mean a reduced, though not necessarily smooth at the moment, proper, connected scheme over k of dimension 1. And its genus, so the genus of C is H upper 1 of C, OC. And if this is sort of your first exposure to some of this material, you should, of course, think of the field of complex numbers, in which case a smooth curve is nothing other than a Riemann surface. So this is a genus 3 curve over C that's smooth. And the class of curves that I'm going to tell you about today, the class of stable curves, is just a slightly bigger class of curves that admit finitely many automorphisms and will allow only nodes as singularities. Let me say that. So a node, P, say, of C. So here I mean a closed point, a k-valued point of C. So over the complex numbers, just a point. So a node is a point P on C whose local equation has the following form. So locally, it just looks like two copies of the affine line, say, meeting transversely. So it's transversely intersecting. So yes, it's very hard to draw over the complex numbers. One typically draws it something like this. So here's a node. Say, you can think of it, and we will soon think of it as obtained as a degeneration of a smooth curve. In this case, you would think of putting a closed curve, literally a curve now, on this Riemann surface, and then pulling it tight until it has length 0, in which case you obtain a degeneration. Okay, so you should not believe this picture literally. It's very hard to draw two-dimensional planes intersecting at a point transversely. So this is the best I can do, but you should think that there's not a tangential intersection, if you know what I mean. This is a transverse intersection, locally modeled in this way. Is it okay? All right. And a nodal curve is one whose singularities are only nodes. So singularities, if any, are nodes. And that's it. Okay. So let me introduce marked points on my curves. So I'll say that x with n marked points is a nodal n marked curve, say, meaning simply that I have a nodal curve x of fixed genus G, and I mark n distinct non-singular closed points. So the PIs are distinct non-singular, that is, not on the nodes, k points of x. Okay? Here it is. So the points we regard as labeled, and the next thing we're going to do is discuss the automorphism group of the marked curve, meaning the automorphism group of the curve that fixes pointwise the markings. All right, so we say, and this is, I think, the main classical definition of this talk, non-tropical definition. So we'll say that this thing is stable So this nodal n-marked curve is stable if and only if, well, its automorphism group is finite. In cardinality, and precisely what I mean is that the automorphism group of X, so those automorphisms sigma of X that fix the marked points pointwise, is finite. So such a gadget is called a stable curve. And the reason we're interested in them is that these form the boundary. Okay, so these form a compactification of the moduli space, the moduli stack of curves. And what's like, yeah, so the main point is that the finiteness of the automorphism group permits the resulting moduli space to have some desirable geometric properties. So this is a stable curve. And so let me continue to treat the subject of stable curves in a sort of elementary and combinatorial way as much as possible. And let's try to describe explicitly the structure of stable curves according to the components. So, okay, let's start actually with the case of smooth curves. Okay, so we're going to work out as an exercise together. What are, if I give you a smooth curve of genus G, say, how many points do I need to throw onto G to rigidify it? In other words, for which n is it the case that your smooth genus G n-marked curve has finitely many automorphisms fixing those n-marked points? Okay, so let's take the genus 0 case to start with. So in this case, you have a smooth curve of genus 0. These are also known as P1s. And we learned yesterday that a P1, so if you mark 3 or more points on a P1, then the automorphism group is finite. In fact, it's of cardinality 1. Another, if you mark fewer than 3 points, it's infinite. So we learned, again, that X of genus 0 with n-marked points is stable if and only if n is at least 3. So with 3 points, you can send them with a projective change of coordinates, PGL2, in other words, to your 3 favorite points, which somehow are always 0, 1, and infinity. And with fewer marked points than that, you have some sort of freedom, so to speak. So this is more or less highly related to what we saw yesterday in Sam's lecture. Okay, so let's, sorry, is that okay? Okay, let's move on. So genus 1. So does a genus 1 smooth curve have infinitely many automorphisms or finitely many automorphisms? That's right. Okay, so so with 0 marked points, so X with no marked points admits infinitely many automorphisms. And we more or less saw this. And in fact, maybe just to make more of a connection with yesterday afternoon's lecture, let me explain this over the, well, yeah, okay, I guess I don't really need to. But let me do it over C anyways, just for the moment. Although I am assuming that K is any algebraically closed field. Let's do it for C. In which case, we saw that these gadgets could be identified with, so you have a complex plane modulo a full rank lattice, so it looks a little bit like this. So here what I'm drawing is the lattice along with a sort of a fundamental domain. And to produce many, many automorphisms, it suffices to take a translation of the universal cover. So in other words, there was a group structure on this gadget once we chose a base point. And if we're interested in automorphisms of the curve that don't necessarily fix the base point, well, any translation by the group action will do. And along those lines, it's conversely true that if you fix at least one marked point, then you've made the automorphism group finite. So if n is at least 1, then, again, still in the genus 1 case, we have that the automorphism group is finite. And again, this is a statement that can be proved more or less using elementary methods. But let me just say it, because I can't resist. Let me say it in the case of the complex numbers. So in this case, what we're asking for, according to this commutative diagram, is a complex isomorphism of this lattice. So some bijection of this lattice that's obtained by a rotation and scaling. And there aren't that many of those. So most lattices, so away from the two orbifold points that were discussed before, most of the time there's only a single involution of the lattice that does the trick, the negation on the group, if you will. Right? So indeed, most of, except for two exceptional lattices, we have that the automorphism group is of order 2. It's the identity and the involution. And there are two exceptions. The square lattice and the, I guess, hexagonal lattice. Okay, this is not my forte. Sorry, the drawing bit. Okay, so let me try to draw this as best as I can. Okay, so these are two different drawings. One of a square lattice, which has z mod 4z, and here we have my attempt at a hexagonal lattice, so z mod 6v. Okay, and in any case, these are finite groups, and that's the thing that counts for us. Okay, and then there's a well-known theorem. Let me call it a theorem. That if the genus of your curve is at least 2, then already your curve has finitely many automorphisms, forgetting about there's no need to add marked points to achieve that. So again, if the genus of x is at least 2, then already x has finitely many automorphisms. And indeed, we saw, I think we basically saw yesterday, asserted that if the genus is 2, then every curve does have a non-trivial automorphism, the hyperelliptic involution. And generically, for genus greater than 2, a curve does not have, only admits trivial automorphisms. But in any case, it's always a finite group. So now we have worked out as an exercise what these stable smooth curves are. Is that fair? All right. So now, what about the general case in which we permit nodes? So let's pass to the nodal curve case now. So let me state an obvious necessary condition for a nodal curve to be stable. And that is that a nodal curve n-marked, x p1 through pn, is finite, implies, certainly, that for every irreducible component, c, say, of x, c together with, so let me write it this way, the automorphisms, say, rho, of C, that first of all fix any marked points that actually fall on C. So rho of pi is pi for all pi on C. And furthermore, this automorphism fixes any of the preimages of the nodes. So let me write it this way. So rho of Q is Q for all points Q that are both, oh, that's not going to be, sorry, I was about to write C intersect X minus C, but that's not exactly what I want. I want to admit self nodes, so that's not quite right. All right, let's do it this way. So let me take, yeah, sorry? Yeah, but I'd rather look at the normalization. Yeah, okay, so that's another way to do it. But I'd rather take, and this will be philosophically at least important to me, if I have some self node on C, yeah, let me do it here. Then I want to consider, I really want to consider the two preimages. Philosophically, this will be important. So I'll consider the normalization map here, denoted C upper nu. Let me call this phi, I guess. And now let me require that for every automorphism of the normalization, I fix every marked point. So let me just bring up the marked points according to the normalization. So by abusive notation, I'll just write this. And then I'll fix every point above a node, so mapping to a node. So the statement is that this is a necessary condition that this automorphism group, like component by component, is finite. Okay, so putting aside the self nodes for a moment, what I'm saying is that the automorphism group of the individual components respecting the marked points and the nodal points is finite. Now, is it clear that this is a necessary condition for stability? Namely, if this whole group is finite, then it can't you cannot evince an infinite automorphism group just on a single component, right? Sorry, is that clear? Okay, good. Now, in fact, it's also not hard to see that this is an if and only if statement. So it suffices to check these finite automorphism groups because sort of the difference between these two can only be some finite extension. In other words, if all of these groups are finite, so if all of the automorphism groups of the individual components, along with their marked points, are finite, then this big group can only be bigger by a finite extension involving some permutation of the nodal or marked the nodal points, along with some possible permutation of the finitely many irreducible components. Okay, is that clear? Yes. Good, all right. So I won't write more in that case. So that observation combined with our exercise gives the following completely combinatorial, I would say, description of a stable curve. So let me summarize then. So we conclude that a nodal n-marked curve is stable if, let's see, first, for every component C of X, such that the genus of the normalization is 0, let's say. So again, we have implicitly the notation, the normalization, which separates the analytic branches of a node. We require that C has at least 3 special points. So we require that the number of PIs lying on C plus the number of, yeah, okay, I guess I should maybe stick to the normalization, but it's not too crucial. So the number of PIs on C, or its normalization, recall that the PIs are non-singular points, so they don't lie on the nodes at all. Okay, plus the number of Qs lying above nodes, so whose images are singular. That the total number of special points is at least 3. And secondly, we require that for every component C of genus 1, the number of special points is at least 1. And when genus of the component is at least 2, then there's no need to make any specific requirements. Actually, if you process mentally requirement number 2, you'll see that it's not that restrictive. In fact, it only excludes a single case, if you think about it, and I'll let you think about it. And that single case is that we forbid x from being a smooth genus 1 curve and n being 0, and that's it. So maybe I'll just write that and let you, if you've never seen this, just think about it. So remark, 2 only excludes, it sounds very general, but it only excludes a single extra condition, and that is x of genus 1 smooth and n equals 0. Okay, so we're precisely excluding, again, say the genus 1 curves which permit infinitely many automorphisms, say by translation.
Are you assuming x is connected?
Sorry?
X is connected?
Yes, always. Yes, yes, yes. Thank you. Other questions or comments? All right. Exercise before going on. I think I've mostly done this exercise for you, but nevertheless, show that stable curves exist. So stable n-marked curves of genus G exist at all precisely when 2g minus 2 plus n is positive. Okay, so the way I phrased this whole story, you can work this out as like a combinatorial exercise. Another way to phrase the whole story is that you say that a curve is stable if the dualizing sheaf twisted by the marked points has positive degree. And that is precisely this condition. Okay, but I'm doing it sort of from the combinatorial perspective right now. And one of the reasons I'm doing this as combinatorially as possible is that I'm about to define a graph, a dual graph associated to a stable curve. And today, dual graphs are going to actually play the central role. So typically in algebraic geometry, dual graphs are sort of, they're sort of receptacles for recording combinatorics associated to stable curves. But today, I'm actually interested in the combinatorics of dual graphs. And so let me introduce those objects now. So dual graphs of stable curves. So I'll continue to assume, just as a reminder, that I'm working over an algebraically closed field, and there are no valuations in sight for the moment. All right, so suppose I have a stable curve. I will associate to it a combinatorial object. Basically, it records the components of the curve and the ways in which they intersect. It also records where the marked points are and the genera. So it's a combinatorial simplification of a stable curve. So the dual graph. Let me rate it G, boldface, is a triple of data. So here, so G is a graph. Okay, so we've seen graphs before. All my graphs will be connected. They consist of vertices and edges. The edges are allowed to be loops. We permit multiple edges between two vertices. So graph theorists would actually call this a connected multigraph. It's connected, say, as a topological space with its typical geometric realization, and it's a multigraph, meaning that I allow parallel edges and I allow loops. All right, so that's what I mean by a graph. IE as shown. Okay, and its vertices are in bijection with the irreducible components of X. And the edges are in natural bijection, in the incidence-preserving bijection with the nodes of X. So in other words, consider a node of X. Now consider its normalization. So either, well, okay, sorry, just it's much more simple. So consider a node of X, and either the two branches lie on the same component or they lie on two different components. So if the two branches lie on different components, say Ci and Cj, just put an edge between vertices Ci and Cj. And if the two analytic branches are in fact the same component, then just put a loop on that component, the vertex corresponding to that component. That's it. So is it clear how this, I mean, I've named two bijections, but I mean the ones that naturally correspond to inclusion of nodes relating to incidence of edges. Is it clear? I'll do like tons of examples. All right, so the marking now, M is simply a function that keeps track of where the n marked points are. So M is a function from 1 through n to the vertices, and it simply sends I to the vertex corresponding to C if Pi is on C. Recall that the marked points are non-singular, so this function is well defined. Ooh. Not good. All right. Okay, and finally, W is a weight function. So it's a function from V of G, the vertices, to the non-negative integers, and it simply records the genus. So the weight of a vertex corresponding to a component C is the genus of the normalization of C. And there's sort of a lot of different terminologies for these gadgets. I'll call them dual graphs. I may slip and also call them combinatorial types. Or if I'm being very careful, I may call them vertex-weighted n-marked dual graphs. And now I'll do a lot of examples, unless there are comments or questions at this point. Okay, so examples. All right, I will propose to fix, for this example, G equals 1 and n equals 2. And I will draw all the different combinatorial types of stable curves of genus 1 with 2 marked points completely for you. And in fact, I'll draw them in a somewhat organized way. I'll draw them with the structure of a partially ordered set on them, which I will explain. So let's see. So here, let me actually start a new board. All right, so these are cartoon pictures over the complex numbers. So here I have a picture of a genus 1 curve with 2 marked points, P1 and P2. Okay, so algebraic geometers often, well, draw these somewhat differently. They'll just draw a curve like that, mark it with genus 1, and mark 2 points. So I'm going to stick with these pictures for the moment. So here is a smooth curve with 2 marked points, and the corresponding dual graph has a single vertex, since there's one irreducible component, and that vertex is marked 1. So this is the way I'll draw the weights of the vertices. So this 1 corresponds to the genus of this component. And there are two marked points. So typically, the marked points will be drawn as little legs or half edges or infinite rays off of the corresponding vertex. So here is my dual graph. It has one vertex and 0 edges. OK, and now you can imagine sort of specializations as follows. You imagine you take a piece of string and you wrap it around your Riemann surface in some way, and then you pull the string until you produce a nodal degeneration. So there are two ways to do this, I claim, in a way that preserves the stability condition. Let me draw them for you, and then we can argue about it. So here's one, and here's the other. OK, so I've introduced one node in each case. And let me draw the corresponding stable, so this corresponding dual graphs. So one vertex with a single loop now on the left. And this vertex has weight 0, so I propose to just omit all the zeros so I'm not going to write the weight zeros. Okay. And on the right, I have a vertex of weight 1 and a vertex of weight 0 with 2 marked points. Is it OK? So I'm drawing what will eventually become a postset, 2 postsets on the left and on the right, and they're in correspondence. OK, and there are 2 more, which correspond to the most degenerate case. OK, so again, these blobs are supposed to represent Riemann surfaces of appropriate genus. And there are 2 maximally degenerate types, that is to say, terminal curves in the moduli space of stable curves. Yes. And let me draw the corresponding graphs again for you. So on the left, I have 2 vertices, each of weight 0. Each of weight 0 with 2 edges between them, right? So the edges are in bijection with the nodes. And there are 2 nodes here. And here on the right, I have 2 vertices, both of weight 0. And the edges and marked points is shown. Is it OK? Yes?
And the definition of M, you mean CI in C?
Thank you. Yeah, I think I had that, and then I erased it, and then wrote it up again improperly. Thank you. OK. Yes? Anything else? OK. So let me just remark for future use that there is a natural Postset structure, partially ordered set structure on these diagrams. And I guess we'll talk about it soon in the case of this combinatorial types of stable curves. So let me draw the covering relations of the Postset, so to speak. And if you don't know what that is, don't worry. I'm going to tell you exactly what these lines here that I'll draw mean combinatorially in terms of the dual graphs to stable curves. So there is, let me remark, let me call it a weight contraction operation, i.e. given a weighted marked graph and given an edge in that graph, we produce a new weighted marked graph, which in fact preserves the property of stability. And it goes as follows, and I'll just draw a picture if that's OK. So there are 2 cases. Either the edge is not a loop, or it is a loop. And I'll do them separately. So if the edge is not a loop, it's incident to 2 vertices of weights W1 and W2, say. And then contraction means to pull the edge together. So you shrink the edge until it goes away, and you identify its endpoints. And the weight contraction part of this definition says that you add the weights. So this is an operation, you can imagine. I've only drawn it locally, but you can imagine that this produces a new marked weighted graph from an old one. In the second case, if E is a loop, Then we shrink the loop, so it disappears completely, and we add 1 to the weight of the base vertex. And now you can see that the weight contraction is an operation that generates a partial order on the stable marked graphs, which I've drawn using these edges in this diagram. Is it okay? So the weight contraction is a combinatorial recording of specializing to a node. So at the moment, I defined these weighted marked graphs as coming from like the theory of stable curves. But it will be convenient for me to consider these as their own object, in fact, their own category soon. So let me just define this again, and I'll define for you the combinatorial encoding of the notion of stability explicitly. So definition, which is sort of a repeat, but nevertheless. So a combinatorial type / weighted marked graph / dual graph and marked graph is a graph G. Any marking function from 1 through n to the vertices of G, and any weight function from the vertices to the non-negative integers. So that's what it is, and we say that GMW is stable if what? So again, I need to translate our notion of stability, which we worked out component by component, into combinatorics, and it is as follows. So by the exercise, it is if the 2G minus 2, where G is the sort of combinatorially encoded genus of the vertex, so 2W of V minus 2, plus the number of marked points landing on V, and then plus the number of half edges, so the number of edge ends incident to a vertex. So this is the valence of V. This is the graph theoretic valence, number of half edges at V. And we require that 2G minus 2 plus the number of special points, so to speak, is positive for every vertex. So that's a combinatorial definition of stability. And let me further define the genus. This is the definition of a genus of a weighted graph, and it's simply it's the sum of the weights of the vertices plus the first steady number of the graph. So in other words, the number of edges minus the number of vertices plus 1. And it's an exercise to show that like if you start with a stable curve of genus G, then you get out, as its dual graph, a stable graph of genus G. Okay, so I'll just write that and then leave it to you. So I think stability we more or less worked out, and the point is to work out that the definition of the genus of a graph is the correct definition. Now furthermore, you can see that these weight contraction operations that I wrote down here, they obviously preserve the marked points, the number of marked points, and it's not so obvious, but it's true that they preserve the genus of the graph. Actually, I guess it's sort of obvious, so we can just work it out. So here, in the first case, we lose an edge and we lose a vertex. And here, in the second case, we lose an edge, but we gain weight. So the weight you can think of as recording an infinitesimal loop, a loop that's been contracted. And we add 1 to the weight precisely to ensure that these operations respect the genus. I mean, that's one way, purely combinatorial, to say it. Of course, the real reason is that we are working towards constructing a moduli space of tropical curves, where a tropical curve, by definition, is one of these gadgets with an arbitrary length function on the edges. And allowing these vertex weights permits us to stay within the same moduli space, MGN tropical. Okay, and so that's what I'm going to define next, unless there are questions or comments. Okay. So, definition. An abstract tropical curve is just a vertex weighted marked graph G, M, W together with any length function. Right, so I'm just calling it a length function because that's how I think of it, but it's any function from the edges to the positive real numbers. And we say that it's stable if its underlying combinatorial type is. And this is, I guess, the key combinatorial definition of the talk. All right. Is it okay? So they're just gadgets like the ones I drew over there with arbitrary, for the moment, length functions on the edges. So the goal of the whatever time I have left is to explain like an abstract procedure of tropicalization whereby one takes a curve over a valued field and produces a tropical curve as defined just over there. Is it clear? Okay, tropicalization then. Yeah.
You only add the information of the length on the edge.
That's right, yes.
With no condition like on this function. I mean, it's totally free.
No conditions whatsoever. Yeah, that's right. So here's a silly example. So here's a tropical curve. Let's put a weight 1 on this vertex. And let's put any edge lengths A, B, and C. Okay, so this is an example of a genus 3 zero-marked tropical curve. Okay, so in practice, in many of your computations, as you go on in computational tropical geometry, these will be reasonable numbers, but essentially they arise as valuations of elements in a certain valuation ring. So if you're working with a reasonable valuation ring, like for example a DVR, then the tropical curves you will be interested in will ultimately have basically integer edge lengths. So I'm about to describe that now as part of a tropicalization procedure. Thanks for asking. Are there any other clarifications before I do that? Yeah?
In the wave contraction operation, the genus is reserved, but the stability not, right?
It is. It is.
But in the upper right example,
Yes. This.
looks like there is a genus 0.
Yeah, so it was important that I said that I count the half edges at a vertex. So a loop contributes twice to this count. Okay, so basically, like, you should believe that this is stable, if and only if you believe that this picture is stable. So let's look at this actual picture of a stable curve in M12 bar. And I say an actual stable curve because there's no moduli associated to this picture. It's a point in the moduli space, right? There's precisely one guy. And you can see that each of the P1s has 3 special points on it. So
Because we are counting twice, that's one.
that's right. But even if you don't believe me, you can work it out for yourself. So what are the automorphisms of this curve? Well, it has to be an identity on this component. This point has to be fixed. These 2 points can be interchanged, but that's only finite. Right? So if you want to build this curve, you have to specify finite, 3 points here, 3 points there. That's no moduli. And then, you have a finite you're off by a finite factor. Is it okay? So that is why here I really count the number of half edges at V. So the valence, graph theoretically, of this vertex I declare to be 3. Yeah. So if I were being really careful, and I might actually be careful later, I would define carefully for you a category of graphs in which edges consist of pairs of half edges. So the consequence of this careful definition would be that this loop is really like the 2 half edges are in some sense distinguished. Automorphisms, flipping loops, exist in the category of graphs. Okay, and that's a digression, so you can ignore that. Great, anything else? Okay, tropicalization. Okay, let K be a valued field, capital K now. And I'm going to make some assumptions on K, which you may complain about. So it's, first of all, assumed to be complete with respect to its non-Archimedean valuation. And I'll furthermore assume that K is algebraically closed. So these are kind of big fields. You can think of CP if you are arithmetically minded. You can think of not the Puiseux series, which are in fact not complete, but you can think of their completion, which is in fact both complete and algebraically closed. Okay, you might complain that these are like unnecessarily huge fields. And it's true that I could do some of this theory with being a little more careful with my ground field. And I won't for a couple of reasons. The first is just for expository simplicity. And the second is that somehow in this business, it's sort of not a big deal to take a huge base change of your ground field. So just do that. So if you have your favorite curve, then base change to an appropriate, algebraically closed completion. Okay, so recall that we'll let R be the valuation ring. So R denotes the valuation ring. Okay. And K is its residue field. Sorry, so K is R mod M, where M is the unique maximal ideal of the local ring R. Okay? And we suppose that we start with, so let me give some more terminology. So suppose I have, so this is just, I'm just going to quickly establish some words so that I can use them. So if I have some scheme over spec R, recall that this is what spec R looks like, as in the last lecture. So I have a generic point and a special point, eta and S, corresponding to the 0 ideal. So the field corresponding to this point is the original field K, and I have the maximal ideal here. So if you have some scheme X, we call this the generic fiber over the general point. And we call this the special fiber. So the generic fiber is, okay, I won't set notation for that. The special fiber I'll denote X